Hello, this is Sean Mullery from Electronic Engineering at IT Sligo, and in this lesson what we're going to look at is we're going to go back to the timer 0 timer, and we're going to try and figure out exactly how much time it takes for the timer to overflow. So we know that it counts from 0 up to 255 and then it overflows back to 0, but exactly how much time does that take? So what we're going to look at first is we're going to just let the program run first of all, and we're going to look at the logic analyzer. Now what I've done, just while that's doing its compile there, you'll remember that I'm counting up as I go, and in my main.c here you can see that I'm putting that count out on port B, and we saw that that was happening extremely fast on our port pins, telling us very little. Now what's important here is that the least significant bit is alternating between 0 and 1 and 0 and 1 and 0 and 1 every time that count goes up, because it'll be a 0 every time the count is at an even number, and it'll be at a 1 every time the count is at an odd number. So we should expect that to be constantly alternating back and forth between 0 and 1, 0 and 1 and 0 and 1 every time the interrupt is called. So if we actually look at that on the logic analyzer, and we do that by going to Window, the simulator, and we'll go to the analyzer here. So I'll just open up the analyzer, and I'll pick a port pin here, and I'm going to pick RB0. Okay. And what I'm going to do is I'm just going to pause it at that, and we'll run again, and we'll pause. And it's not actually coming up now, so what I'm going to do is I'm going to do a stop, and then we'll run again. And that way then we'll be able to see it on the actual simulator itself, or on the logic analyzer. So we'll just pause there, and now we can see the signal coming out. Now what I'm going to do is I'm going to zoom in on this. I'm right mouse clicking, zooming in, and looking at the domain axis zoomed in. Now just by getting a rough idea here, we can look at the timings here, and we can zoom in even further to get a more accurate sort of a look at it. Okay, so if we look at the amount of time that it's either switched off or switched on, we can see that it's gone from about somewhere between 674,850 and 674,900 there. So it looks to me like it's around about the 880 there, maybe, that it's starting. It's actually, if I actually hold the cursor over it, we can see it there. Okay, so it's 881 there, and on this side it's gone up to 134. So from 881 up to 134. So if you have a calculator, grab it. 134, and we'll take away 881, and that's coming in at around 253. Okay, so, and that's all to do with the accuracy of where I'm actually holding the thing over it there, and so on. Okay, so this is actually instruction cycles that we're looking at here. It's not time. And so what we have to try and figure out then is, when we're dealing with this, is how long is an instruction cycle? So I'm just going to zoom out there a little bit. Okay, so how long is an instruction cycle? Now if we look back at the document here, and we actually type in instruction, okay, and this will pop up quite a lot, so it could take us a while before we find the one that's of interest to us. So what we might do is we might pop back the way, and maybe it might be at the beginning of the diagram, or of the thing. And in fact, there it is written there. Okay, so the 1/4 of the frequency oscillator, and this denotes the instruction cycle. So what that's basically saying is that whatever our oscillator frequency is, let's say our oscillator was 4 megahertz, that would mean that our instruction cycle would be 1 megahertz, and that means that every instruction would happen in 1 microsecond. Now if we have a 12 megahertz clock on our system, that means that that would be 12 megahertz, divide that by 4, that's 3 megahertz. That would mean that our instruction cycle was once every 1/3 of a microsecond. Okay, so you can always work your way back to timings given the information that we have here with regard to the number of instructions. Now, what I'm going to do is I'm going to look at how would we decide that we wanted a particular, rather than just having it that it was every 255, what if we wanted something different than that? So let's assume that I wanted to have the counter go up not every 255 or 256 instructions. I wanted to have it change every 100 instructions. How would I do that? Well, the timer register has a register called T, M, or 0. You'll have remembered this if you go back, or you can go back and look at the document on it. This is the actual register that holds the 8-bit number that counts that the timer increments as it goes up. And what happens is it will go from 0 up to FF, so it always counts up the way, and then it overflows. Now, what we want to look at is we want to get 100. So what we really want to do is we want to start it off at a value of 155 and let it count from there up to 255. That will be a move of 100 instruction cycles, and that would then mean that we would interrupt every 100 instruction cycles. So what I'm going to do, and the easiest way to do it, is if we wanted to work for 100, rather than constantly trying to calculate it and saying I'm going to set that to 155, what we will do is we'll say, well, the upper number is 0x FF, and I'm just going to subtract the number 100 from that. Okay. Now I know I'm using hex in one place and a decimal number in another place, but that's okay. It accepts both of them, and we're just going to subtract the 100 from that. That means that we will automatically be at the right value, that it will count up 100, so that we can actually get 100 cycles each time. So what I'm going to do there is I'm just going to run that. And we're going to have a look at the output and see does it change, that it should be changing back and forth every 100 cycles. Okay, and already it does look a little bit narrower, but that could be just to do with the way it's been the range has been set for the zoom. Okay, so something strange going on here, or a little bit strange. We can see there that if we take this one, which seems to be almost exactly on the 700. Now I'm a little inaccurate in where I'm actually holding the cursor there, but it looks like it's sitting pretty much on the 700 there, and we can clearly see that it's gone well past 800, and it's not until here that it's changed. And again, the same for the higher side. Again, it's gone well past 100 cycles in that direction as well. So the question here is, have I actually made a mistake? It looks like that's around about 120 rather than 100. Is there a mistake in what I've done, or have I just not taken account of something? Now, as it happens, it's that I haven't taken account of something rather than I've actually done something wrong as such. So what we're going to do is we're going to take we're going to investigate why exactly it is that we're not getting it in this amount of time. And the way we're going to do that is that we're going to put a breakpoint here on the count, so that as soon as we've set this to the 155 and gone to the next instruction, in fact I'll put a breakpoint on that one as well, that might be the better place to put it. As soon as we've got to this breakpoint, we'll hit the next instruction. That will put that value in there, and what we'll do then is we'll watch that value rise all the way to 100 and see what occurs and see why it's not changing then at that point. So I'm going to stop the running there. Okay, So I've executed the program, I've run as far as this point, it's come to a stop, and what I'm going to do is I'm going to look at the special function registers. Now if you don't have that window, don't worry, it's just up here. You go to Windows and you go to Pick Memory Views and Special Function registers. There it is, SFRs. Okay, and the SFR that I want to look at is the actual TMR0. I want to find that in my list so that I can get an idea of what value is in it. Now you'll see, and this is actually a bit of a giveaway, the number 20 is in it at the moment, which is actually as far out as I thought I was the last time when I wanted it at 100 and it was actually at 120. We'll come back to exactly how it's ended up with that in a moment. So I'm going to move to the next instruction. And as you see, the number 155 has gone into timer 0, and that is the number that we put into it. That's where we want to start. Now what I'm going to do is I'm going to keep stepping through it. You can see that that's the F7 key. So I'm going to keep hitting the F7 key, and we're going to watch. We've come out of the interrupt. We've gone back to putting something into port B, the counter and so on. And if you watch the timer 0, it's not going up in ones, and the reason it's not going up in single values is that each of these, the while and so on, they take a number of instruction cycles. They're not just done in one individual instruction cycle. So we'll keep going there. So we've gone up to 191, 193, 197, 199, 203, 205, 209, 211, 215, 217, 221, 223, 227, 29, 33, 35, 239, 241, 245, 247, 251, 253, and we've overflowed. So we've gone from 253 past 255, we've gone back to 0, and we've got back up to number 3. Now we're in the interrupt. So the cause of the overflow has occurred. We've gotten to the interrupt, but the thing is, it's taken a number of instructions to get to the interrupt. When an interrupt service routine is called, it has to do a little bit of housekeeping before it actually gets from the main program to the interrupt service routine. That takes a number of instruction cycles. We can see that it's taken at least 3 instruction cycles at this stage before we've even got to the interrupt service routine, because the timer has overflowed and it's still going. Okay, so let's hit F7 again and see where we move to next. We've got as far as the if statement, and timer 0 has gone to 17. So we've clearly seen that in the jump from this, where we've jumped as far as the interrupt down to there, we have already lost 14 instruction cycles. Where exactly have they gone? Well, they've all gone on the interrupt doing a little bit of housekeeping. What occurs is that the interrupt needs to remember where it has to get back to, so it needs to save a certain amount of information about what was interrupted when the interrupt occurred. It needs to save a certain amount of that information. That takes a certain amount of instruction cycles to occur. So for us to actually get to the point where we're executing our interrupt service routine has taken, you can see here, 17 instruction cycles. I'll hit F7 again, and what I've done now is I've zeroed the flag, and in zeroing the flag and doing my if statement, I've now gone to timer 0 has now gone to a value of 19. Finally, at 20, I've gotten to the point where I'm going to reset it to 155, and then I've moved on, and I'm now at 155. So what that has showed us is that we wanted this to change the value on the port, in other words the counter. We wanted to do that every 100 instruction cycles. What we didn't take into account was that when it did its 100 instruction cycles and caused the interrupt, there was another 20 cycles had to take place before I actually got to the point of making my change. So this is an overhead that's always there, and if you think about a situation where you might have a you might be looking for a 50 millisecond delay or something like that. 20 instructions, if you're using a 4 megahertz crystal, you'll only lose 20 microseconds. It may be not a big deal. If you're using a faster clock speed than that, you'll lose even less time in that. So your timing will only be out by a very small amount. But it's at these very precise amounts we can see, and that's why I've gone for such a small number, we can see that it has an actual quite a large effect. What am I going to do in this case to solve the problem? Well, what I'm going to do is I'm going to compensate for that. I'm going to put this to 80 instead. Okay. Now we may find that that's not exactly right, that I need to set it to 78 or 82 or something like that, because you may remember previously we said that when you set the value, the timer stops running for 1 or 2 instruction cycles. But I'm going to set it to 80 for the moment and see how close that gets me, and that might be enough for us to do. Okay. So what I'm going to do is I'm going to get rid of the breakpoint. We're going to run the program again, and I'm going to look at my logic analyzer to see how well I've done this time. Okay, so my program's run there. There's my logic analyzer. I'll hit pause on it, and I'll now zoom in. Okay, we can see that this is looking pretty good. I've gone here to a high point here, and that's at just below 850, and I've gone low again just below before 950. What we notice though here on the other side is that I've stayed low for just below 950 to just above 050. Okay, so we can clearly see that in certain circumstances it seems to be working pretty okay, and then in other circumstances it's not quite. In other words, it seems to be spending longer at the off stage than the on stage in this particular section. Now the reason that that can occur is that it really depends on where the main program actually is when the interrupt occurs, as to how much information it's going to have to save and how difficult it is to move to the interrupt. So we'll never get it perfectly right when we're doing these things, but we can get it reasonably close. And depending on the application and how accurate your timing will have to be, that's probably as close as you're going to be able to get to an exact timing. Remember, we're down to individual instruction cycles here, so we're down to a small number of microseconds, depending on what your processor speed is. So generally speaking, that would be okay. If you want much more advanced timing, the chances are you may have to use a much higher clock speed, in other words a much higher oscillator speed, or you would have to use a more advanced processor than that. Okay.